everyone, welcome back. This is Judy Warner for this week's Ecosystem Podcast. You won't believe who I have for you today, someone I haven't talked to in a long time, and I'm sure you're going to completely enjoy. Today I speak with Rick Hartley, and we're going to talk about 5 upcoming talks he has at PCB West, which will take place in Santa Clara, October 4th through the 7th. He talks a lot about grounding, but also switch noise. He talks about IoT, about mechanical design, and so much more. But he's going to give you some specific takeaways around grounding in case you can't attend that conference. We also talk about the recent acquisition of UP Media, the planners for PCB West, by PCEA. Rick is one of the executive members of this engineering organization, and I think you're really going to enjoy what he can tell you that was happening behind the scenes and all the value this organization is bringing to the industry. Make sure you check out the show notes. Of course, I've always loaded it up with good resources for you so you can go dig in a bit deeper, including the registration link for PCB West. I will be there, so if you're joining, please stop me and say hello. I look forward to seeing you, and also Rick Hartley at PCB West. Let's jump in now to our conversation with Rick Hartley. Hi, Rick. Thanks so much for joining us. I can't believe it's been so long since we've done this.
It has been. Good to see you.
Good to see you. COVID wrecked everything, I swear. So anyway. Yeah. Well, Rick, I wanted to have you on because I know PCB West is coming up in Santa Clara, October 4th through the 7th. And I keep seeing things on LinkedIn and out there on the internet that you're doing several talks there. So I wanted to get you on and hopefully encourage some folks that are here in the U.S., that they could attend. So before we get going, why don't you give the, 2 people who don't know who you are a brief background, and then we'll jump into your talks.
Okay. For the 2 of you. I've been around electronics since 1965, began life as a technician, over time studied, became a double E. Along the way, I laid out some printed circuit boards, and 12 years into my career, I was asked if I could help with the printed circuit design group in the middle of an engineering design project. And I said, sure, I'd be glad to help. And after 6 months of doing that, I decided I preferred circuit board design to circuit design. So I jumped into that arena. That was in 1977, and I've been doing that ever since. Somewhere in the 1980s, we started having noise problems in circuits, and no one in our company, no one, myself included, understood it. And I made a decision that I was going to figure out what was causing these problems. And over a period of 10 years or so, I did. And once I got a grasp of it, I began to realize this is really not all that hard to understand. And so I started putting together classes on both signal integrity and interference of all types, including EMI, and began teaching in the late 90s and have been doing so ever since.
And you're quote unquote retired, but
yeah,
I think you've been busier post-retirement than you were.
I think so. My goal in 2015 was to, cash in my chips and go sit by the pool or whatever. And it
Right.
just didn't work out that way. I've gotten a lot of calls and emails for people who want my help. So I just continue to throw my 2 cents in.
Well, it's amazing that those problems since the 90s, and they seem like they're just getting worse because of speeds of technology.
Yep.
And every time we make a jump in speed, it adds a different set of variables in. So anyways, it's wild that it's continued to persist this way. And I think your perspective as an EE, because of course, none of this is taught formally.
Right.
And it's sort of this tribal knowledge, but it's so valuable.
Right.
And that's evidenced by, again, how many talks you've done and how popular, and, our time at Altium Live,
Right.
you keynoted, I think, every year, and people just ate up the knowledge and would walk away saying, why did I never know this? And tell people how many books you read in your journey of self-education.
Yeah, it's funny. In the 80s, when we were having problems, the first book I believe I bought, if I remember correctly, was Henry Ott's first book, with the name of which I can't remember. He rewrote that book later and called it electromagnetic compatibility engineering or something to that effect. He doubled the thickness of the initial book and then updated the initial writings and so on. I bought that book first, and just started buying books after that. And the last book I bought was like number 122, I think, or something to that effect.
Which is
I've got a huge bookshelf just crammed with books. And I've read them all, some of them 2 or 3 times. The really good ones I've read several times, and they're dog-eared to no end. As you can imagine.
well, and I think that is such an important point. Not only is it impressive that you did that and you continued on the path, even though you're an EE and had years in the industry, you worked for L3 doing really difficult, challenging designs, but it's the importance of continually self-educating, right?
Yes.
Because technology is changing all the time. So, anyways, to our listeners, take a page from Rick Hartley's playbook. Let's talk about PCB West that's coming up in early October. When we were speaking recently, I didn't know you were doing so many talks, but I think you're doing 5, correct?
Correct. Yes, 5.
Okay, why don't we give a sneak peek of the 5 courses that you're teaching, and then we'll dig into those a little bit.
Okay. The first one on Tuesday is on Tuesday afternoon. It's a 3.5-hour class on grounding to control noise and interference, signal integrity, the whole gamut of issues. I did, as you know, I did for Altium in 2019, a 2-hour video on that same subject. It's online, and a lot of people have viewed it. There's like 175,000 views of that silly thing. It's amazing how many people have watched that.
Well, and that's the point. Like, it's so valuable, right? And
Well,
I know it clearly was evidenced by the number of views and also all the comments. So I'll for our listeners, I'll throw that in the show notes.
Okay.
But also, if you just Google or go in your search engine and write Rick Hartley grounding,
that's it. That's all you have to type.
That's all you have to type. And I'm sure some of his other videos will come up. So if you don't have the opportunity to come to PCB West, dig in. You'll love it. But obviously you can go a lot deeper in a 3.5-hour course. So
yes, and that's exactly the point. This 3.5-hour class, we're going to go deeper. I'm going to delve much deeper into circuit board stack-ups and the impact they play. The class is called grounding, but in reality, what does that mean? Well, there are 3 things in a system that we call ground. One of them is the earth, which is the actual ground. And another is the chassis. When you have a metal or metallized chassis, people tend to refer to that as chassis ground or earth ground. And the third is the plane or reference planes within the board. And all they really are reference planes. They're not ground. They're just reference planes. Even if you attach them to the chassis and then attach the chassis to the earth, they still are not at ground potential, because it's very challenging at the frequencies where we operate to get a low impedance attachment over those lengths of feet of length or meters of length from the unit to the earth. It's very challenging to get a low impedance attachment to the earth. The reason we attach a system to the earth is safety. That's it. No other reason. People think, oh, I have to attach to the earth to pass EMI. Your cell phone passes EMI. It's not attached to the earth.
Very good
The
point.
avionics equipment didn't have a wire coming out of the airplane going to the earth somewhere. And all of those pieces of equipment passed EMI testing eventually, some of them not right away. That's a tough market. It's like the automotive market and some of the other markets that have stringent requirements, obviously.
Right.
But so that's one thing. Earth grounding a system to the earth, attaching it, is almost always done for safety reasons.
Interesting.
The chassis, what we call chassis ground, when people attach it, they say, oh, it's chassis ground. Well, it isn't really. It's the chassis, when it's metal, is a Faraday cage. And if it's designed correctly so that there are no major size openings, and I'm doing, by the way, another class at PCB West called Mechanical Design to Control EMI. And that's exactly one of the topics it deals with, is how big can an opening be relative to frequency? How do you determine frequency? Is it clock frequency? The answer to that is absolutely not. As you well know, Judy, it's rise time frequency.
Yep.
What is the frequency associated with the rising and falling edges? And that's one of the things in the grounding class that I'm going to go into much deeper detail than I did in the 2-hour class is how do you determine what the exact frequencies in your system are? I kind of touched on that in the 2-hour, but I'm going to go into a much deeper dive, tell people where to get the rise and fall time information and how to calculate all of that. So anyway.
Oh, it's on the data sheets, right?
Yeah. Okay. Yeah, of course. Yeah. And that's the sad part. It isn't on the data sheets because rise and fall time, there's no one number. There are min and max and typical numbers for rise and fall time. And people who know what they're doing will take the worst case condition and use that rise and fall time as their to calculate frequency, because obviously if the IC lists a worst case condition, it can get there. And even though the typical ICs won't, if ICs can and you don't account for that, well, then you see where you're going to end up. So somebody's going to install ICs that do go to the max condition, and they're going to have problems in the field, signal integrity or EMI or interference of some form, and they'll be in DPO group. And so we're going to talk about how to calculate all that. But again, it's really a rise time thing. And back to your comment, it would be nice if it was easier to find that data.
Yeah.
But it isn't. It's not a, oh, here you go, just go to that app node or data sheet and voila, there it is. It's not that simple.
Yeah. And I'm sure there's a lot of things that contributes to that, right? Yeah. And if this, then that, and you know.
Sure. Yeah, there are a lot of things. There are a lot of ifs and ands that come into play about when you do what and why you do it.
Yeah. So it's not just, if it was easy, everybody would just do it and understand it. And the sad disconnect between, say, someone just doing exclusively PCB design and not being aware or not having enough situational awareness. There's a million things that can, blindside you and then send you on a, fishing expedition, right? That's not fun, I'm sure.
I mentioned Henry Ott a minute ago. Years ago at PCB East, he was doing a keynote, and he attended my 2 or 3 hour EMI class that I was doing there. And afterwards, he came up and we talked, and he said, "I'm glad you had this book and that book on your reading list." He didn't comment on his book, of course, it was there too, but he said, "I'm glad you had Ralph Morrison and all these other people." And I said, "Henry," I said, "you've been credited with your 1976 book, writing the first book on EMI control." And I asked the question of him, if you wrote the first, how did you figure this stuff out?
Good
and
question.
He said two ways, basically. He said, we were frequently stupid. And he giggled when he said that. And he said, meaning, of course, that we made lots of mistakes and we stepped on our own toes. We eventually learned to dance and not step on our feet or our partner's feet. And it took time. It took us time to figure out, why are we failing? What's going wrong here? Where's the energy coming from? What's the source? How's it getting out? What's the antenna? What's all of this stuff? And he said, time and trial and error taught us a lot. And that's what was in his first book. And he said, additionally, he said, one of my greatest sources of knowledge was Ralph Morrison's 1967 book, Grounding and Shielding. And people ask me all the time, God, Rick, if this problem is relatively new because of fast rise times, how did Ralph experience this stuff enough to write a book in 67? And the answer is he was dealing back then with transmission lines that went between buildings and between complexes across miles of distance. So even at the slow speeds of those days, when you're covering miles of distance, those cables are hugely long compared to wavelength of the signal. Therefore, you experience all the high-speed effects that we experience today within systems and within the cables and systems.
That's fascinating.
Isn't that fascinating?
Yeah. And it's like, and thank goodness.
Yes. Yes,
right?
Ralph was one of my greatest mentors.
And
He,
I
as you
know
know,
Dan
passed away a
Beeker.
few years,
Yeah,
and Dan.
boy, what a loss. And I know
Oh
both
God,
you and Dan Beeker credit his knowledge, but that's an interesting backstory.
yes,
Um, all right, tell us about where I want to ask you, for our audience, I want to give them a couple tangible takeaways if they can't join us at PCB West. But let's talk about briefly your other classes that you're teaching, Rick.
sure. So I've got Wednesday off. Yay! I actually get to attend other classes this week.
What?
That's great. Yeah, I know. Yeah. Anyway, Thursday morning, I'm teaching a class on switch mode power supply layout. And the reason for that class is several things. The very first switcher that I ever encountered was about 30 years ago. And the layout of it was so hideous. Not only did it have EMI problems, it physically wouldn't function. The switches wouldn't continue to switch. We would goose the thing and get it started, and it would run for a short while and then just die. And it all had to do with circuit board layout. There was nothing wrong with the selection of components. It was purely a circuit board design problem because switchers are very sensitive. And people think, oh, why do they create EMI problems? They only operate at a few hundreds of kilohertz or a few megahertz. Well, they only operate at those switching speeds, but the rise and fall times of the FETs are extremely fast, which gives us energy levels well into the hundreds, sometimes close to the gigahertz level frequencies, just because of rise and fall times.
And wasn't that sort of the smoking gun you found back when you started trying to figure out the noise issues you were having?
That was exactly it. Everybody kept saying, well, the clock frequency is this and the clock frequency is that. Why are we seeing this problem and that problem? And oh, if it's the clock frequency and it's 25 megahertz, why are we seeing problems at 386.7 megahertz? That's
Right,
not a harmonic of the clock.
right.
And the reason, of course, we eventually figured out was that it was related to rise time.
Rick, I've shared this before on the podcast, but I don't know that I shared it with you. But I find it fascinating because, my background is strictly in the PCB. And
Right.
in today's technology, it seems like such a humble, piece of the puzzle. But I was talking to Steve
Mhm.
Sandler, who you know of, a power integrity guru, and he was telling me when he was doing the power modeling for the International Space Station.
I know, that's amazing.
Right. I know. But on every page of his documentation, he had a stamp that says does not include board effects because he says board effects didn't matter. And now he says now everything is board effects.
Yeah.
Okay. Well, if this is not widely understood, how much are engineers chasing their tail today? Right.
Unfortunately, a lot.
And that's just so, anyways, I love having people like you and Steve Sandler on to say you won't believe it.
Right.
Right.
It's the parasitics of the circuit board, the capacitance and inductive effects of traces relative to each other, relative to return paths, relative to power delivery. All of these things impact each other. And those parasitic elements have a major impact on performance.
Yeah. So, anyways, I'm always amazed because I always think of the semiconductor like the sexy, complex, you know, money place to be in the electronic space. And it's like, boy, that it all comes down to board effects just kind of amazes me.
Well, that's interesting you say that because one of the things I'm going to talk about in that grounding class at
Hmm.
PCB West is the impact that ICs themselves have.
Yeah.
Because the IC is physically small enough relative to frequency associated with rise time that the IC itself typically doesn't resonate and radiate and cause the problem directly. What it does, however, is couple its energy through these parasitics to the
Mm,
circuit board, and then the larger features on the circuit board will resonate and radiate at the frequencies that were pushed into it by the IC. So even so,
mm.
it does come down to the fact that ICs are often the direct problem, but they are the problem indirectly because they push their energy into elements which can resonate and radiate.
Steve was telling me that he was showing me, I don't know, some kind of IC or chip. And he says that he worked on a particular chip that had 80 power supplies inside of it.
That's nuts.
That's nuts. And he says, and they're all little antennas.
Yes. Yes.
Yeah. So this bridge between the parts and the board
Right.
is not intuitive, right? And so that's why I love to hear what you teach. Is this all about the fields, right?
And it's interesting. The kinds of ICs that Steve is talking about
Mhm.
are ones that are getting fast enough where they are becoming not the indirect problem, but the direct problem.
Yes.
I said a minute ago, a lot of ICs don't directly resonate and
Yes.
radiate, but
Yes.
they couple their energy.
Yes.
The ICs that Steve is talking about, those are ICs that will not only couple, but will directly radiate the energy out of the system.
Yeah. Which I
things
think,
are getting blindingly fast.
right. And blindingly complex, and how to
Yes.
simplify them and how to equip.
Good.
Well, again, that's why I named this the ecosystem with the double E, because it all starts there, right? And
Right. Oh, yeah.
having that cross-functional or cross-disciplinary awareness, you don't have to be a super pro about every little aspect. I mean, who could do that? I mean, systems engineers get pretty good at that, but
Right.
it's like filling those gaps of like, why is this doing that? And so, you and I both share that
Right.
passion. And it's
Right.
so funny how much we talk about boards, which to me is not an intuitive place you'd go right
Well,
away.
Yeah,
Anyways,
as you know, in the 60s, 70s, and even most of the 80s, the circuit board had little impact
yeah.
on behavior of the circuit. And that's why it was taken for granted for
Mhm.
so long,
Yeah.
because it didn't impact anything, because
Right.
its size and the features on it relative to frequency wavelength were minimal enough that who cares?
Who cares?
We broke every law of physics known to humankind back then and got away with it because we could. And eventually it caught up with us.
Yeah. Well, anyways, I'm sure people are going to love hearing. Well, okay, let's dig into some of your other classes. So grounding, switch mode,
Mode power supply layout, correct?
power supply layout.
Mhm.
I think you have one on IoT.
I do. It's actually a class that's dual. It's a dual class. It's on IoT design, but it's on board design for IoT. But it's
Okay.
also dealing with 1, 2, and 4 layer boards, because and I call it IoT and low layer count, because most IoT boards, for cost reasons, are 1, 2, and 4 layer boards.
Mm-hmm.
And they're to just lay out a 1, 2, or 4 layer board and make everything have a good reference and contain fields and not have signal integrity, any of my problems, is not a la-di-da issue.
Mm-hmm.
It's a challenging issue. I remember one time back in the late 80s, one of the people in the company where I was working came to me and said, ooh, if we need help in board layout, there's this company here that's a service bureau in town. They can even do multi-layer boards. And I said, what do you mean even do multi-layer boards? And he said, well, isn't that challenging? And I said, no, that's the easy way out. I said,
Wow.
the more layers you have, the easier it is to do and get it right.
Yeah.
It's small numbers of layers that are challenging, not large numbers of layers. And so
Right.
that's why I've put this class together, because I want people to understand you can get impedance control, you can contain fields, you can lower or eliminate EMI issues if you do everything correctly. And
Well,
that's what this class is.
Okay, I want to ask you about that. So, in my, 3-inch deep, sense of engineering, something was occurring to me, Rick, and I know you have a lot of history doing RF boards, right? RF
Right,
and maybe
yes.
microwave frequency boards. So now that everything's IoT, even though there's a low layer count, right? Isn't that like everything's talking to everything, right?
Unless you do it correctly, that's correct, yes.
And so it appears to me that there needed to be more knowledge. And now engineers that haven't had to design, say, in RF and they may not know the landscape of how different that is. Is that
Right.
true? Or is that just,
Oh, it's absolutely true, because prior to being thrust into those arenas, people could get away with lesser,
Mm.
with lower quality practices, with not having good enough references for everything, with
Mm-hmm.
not doing a good enough job of power delivery. When it comes to EMI, power delivery is probably 75% of the problem.
Wow.
And so many people have no idea that that is true. And when you get into low layer count, it becomes that much more challenging to do this, do it well, and do it correctly, and eliminate the problems. Yeah.
Yeah, it just seems like an opportunity for a mess to me. But
Oh, it is.
okay. Yeah, I mean,
And
that's
people who
kind of
jump
what I
in,
thought.
sorry.
Because Rick, I worked with Transline, who's the sponsor of the podcast now, right? And I sort of went down this rabbit hole of how different RF microwave and certainly now millimeter wave technology at the board level are so radically different.
Right.
And my background in boards, I didn't realize how the boards were made affected the performance, but we could be like inside IPC specs, but still jack the performance by accident. But Transline was really good at that. So, and then I had to learn about materials and I had to learn about so much. And I realized, oh my gosh, I don't think engineers realize this. And then IoT exploded. And I'm like, uh-oh, what don't the engineers know and what don't the manufacturers know? And it could be deceptive because of the low layer count.
Right.
And like Rogers 4350 doesn't act that different than say FR4. But if you take a tiny step up, then it acts really different.
Right.
So anyways, it just seems like a mess to me, but I don't know that for a fact, but I just wondered because you're teaching that class.
Yeah, no, it is. The potential for a mess is there. And you're right about 4350. If you, because of its E sub R and other characteristics, if you're dealing with frequencies up to maybe a gigahertz or two, it's really not that much different than FR4. Where if 4350 becomes golden is at really much higher frequencies. And it's because it has much lower loss tangent characteristics, and some of the overall losses of the material are much improved over FR4. And it's easy to work with. You can bond it with FR4. We used to do a lot of mixed material designs at L3, where we would put Rogers 4000 on the surfaces, and then everything in between was FR4.
Yeah, Transline did a lot of that too. What we call them hybrid boards, right?
Yes.
And it's cheaper, right? And so you could use the more expensive layers for Rogers, but then you can use FR4 for the less critical.
Right. And we would mix analog, high frequency analog with digital. And we would put all the digital stuff in the FR4 layers. I mean, the components would be on the surface on the high frequency material, but all the routing for the digital would be on the FR4 layers.
Yeah.
And all of the routing and components and the waveguides and all of the things that mattered for the RF circuits were all on the surface layers where the high frequency material was.
And my observation, if you just say, because whatever insertion loss or whatever it was that you needed performance wise, if you just took half a step above in performance wise in Roger material, because 4350 is very stable, you take one little step up and you're in a whole different playing field, but it may not look like it.
Right.
And an engineer is going for the performance, but anyways, it was one of those blind spots.
Yeah.
I remember teaching a class once at PCB West, and again, our listeners have probably heard me told this story once before, is that there was a really talented RF and microwave board designer that used to call himself the PCB janitor because he was always cleaning up other people's messes. And I know. Good. And so he and I talked about all these pitfalls and I would teach him about the board fab side and he would teach me about the layout side. And so we really enjoyed giving that bi-directional input. We ended up just doing a free talk called Navigating the Pitfalls of RF PCB Design and Fabrication. Never done a talk
really
there.
Neat.
And it was free. And I thought, well, we'll see. luckily no one's paying for it. Rick, over 100 people showed up and it was standing room only. And I went, ding, ding, ding. We found. So, Rick, you should do this class with Jerry Partita.
Jerry and I, it's funny you mentioned that. Last year at, might have been at East or was it West, one of the two. We talked about doing a class together, and I would like to pursue that. I've been so busy that I haven't followed up, and neither is he. He's probably even busier than I am. Jerry.
I'm going to bug you guys because because I always have great plans for other people's lives.
Yeah, well, no, that's okay.
I think that's so valuable. And for our listeners, if you think that's a good idea, drop some comments, on YouTube or Apple Podcasts, wherever you find this, just to take a straw poll if that's of interest. Because again, it's something, I'm putting my finger to the wind a little bit, but from that experience, and then we were like petrified to do it, like hoping that we are equipped enough, but you could see, that I think there's some gold there and you could do it. You and Jerry, for our listeners, Jerry Partita works at Summit Interconnect, and he's, decades in front end engineering of the board side. So you take an engineer and you take high-end engineering, high-end front-end engineering at a board shop, and you put those pieces together and you start seeing where all the pitfalls are, and you start getting tangible takeaways, for best practices and avoiding those pitfalls. So anyways, I'm going to bug you guys about it because I think it'd be really valuable.
Jerry is a special guy. I really, really admire him.
Yeah, he's great. He's taught me so much, and
me as well.
Yeah, I know. He's a great resource. Summit is also a sponsored podcast, by the way. And this is why I picked these people, because they're helping fill those gaps. So, okay. Another talk you're doing, I think, has to do with mechanical design, which I don't know that I've ever heard you do a talk on that subject.
I last did it in 2017. I've only done it, I think, twice in the history of PCB West. Did it way back in the day, and then again in 2017. It got good responses, but we just, for some reason, hadn't done it in a while. And it really deals with the mechanics of EMI, meaning what impact does the overall enclosure have on EMI? What can you do at the enclosure level to help control EMI? Things like board shape. What impact does board shape have on EMI? Believe it or not, it does have an impact. Yes.
You see my head like the.
I know.
I'm like, what? I've never.
I know, and a lot of people react that way. Longer, narrower boards tend to, per given layout, tend to have greater EMI signatures than boards that are more square. And I'm not completely sure why. Well, I think I know. And I think it has to do with fringe fields in power delivery, because of when you move energy in the z-axis through a circuit board, as you go from this signal layer down to this signal layer, you have to move the energy from that top dielectric, because as you know, the energy doesn't flow in the copper, it flows in the plastic of the board.
Right.
You have to move it from that top dielectric down to a different dielectric. And in doing so, you have to move it through the z-axis. Right. Well, if you just put a signal via in the z-axis and don't have some path for it to couple to, then the fields, every dielectric layer it goes through, the fields spread out in the X and Y direction. All those fields couple into each other in common mode, which can lead to EMI risk. But not only that, if the board is small enough, the fields can expand all the way to the edges and cause what's called fringing off of the edge of the board.
Interesting.
There have been several papers done on this, and I quote 3 of the multiple papers in my current grounding class. That's another thing that wasn't in that 2-hour class from 2019. What I'm going to talk about in this class is I'm going to give reference material for people to look this up. There's a paper by Istvan Novak and his colleagues on that subject. There's one by Steve Ware, who I don't know if you remember Steve Ware, brilliant guy. Sadly, he passed away a few years ago. Just an absolutely marvelous man. The greatest paper I ever read on correct use of ferrite beads was from Steve, and it's one that Lee Ritchie and others reference constantly because it was just such a brilliant work. Anyway, Steve wrote a paper on fringing fields and z-axis effect, and there have been others as well that I reference in the grounding class. And the bottom line is, when you have a longer, narrower board, you're more prone for those fields to expand to the edge. And that's simply a guess on my part, because I've never seen a written analysis of why squarish boards are less of a concern than longer boards.
I have never heard that, but at least conceptually, the fringing fields make sense. I was going to ask you if they radiate off the board, but no, there's nothing for them to be attached to. But
and it depends, yes, it depends. Those fields at the edge could couple into something.
That's what I'm wondering.
Is into cables? They could.
That's what I was wondering, if they could couple off the edge of the board. Interesting.
Or into a slot in the box.
Interesting.
Think about that.
Okay. You always have a way of making my brain virtually explode a little every time I talk to you. No, I love it. I love it. I love what I learned from you. And you describe it in such a way that I get it, which is good.
Another thing that's in that mechanical class, where should I/O connectors be? This is something most people don't know, but if you put I/O connectors on more than one edge of a circuit board, it increases the risk of EMI.
People do that all the time.
Oh, absolutely. It's a terrible practice. And I'm not only going to show why, I'm going to explain why, and go into the physics behind why this happens.
Well, Rick, now I want to attend all your classes, dang it. So I hope that means our listeners will.
Good, yeah, me too.
Okay. And then the last talk I think you're doing is on DDR 2, 3, and 4. So talk to us about that.
Yeah, DDR 2, 3, and 4. It's actually going to cover everything from DDR 2 beyond. I first got interested, I've done DDR memory routing a bazillion times in my life. And I just always read the specs and and not the app notes, but I read the specs like the JEDEC standard and all that kind of stuff to figure out what the intent of each iteration of memory. So when they went from DDR 2 to 3, what is the expectation? How much headroom do you have in terms of noise? How much headroom do you have in terms of timing? All of these kinds of things. And one of the things I discovered going from 2 to 3 was that in DDR 1 and 2, everybody would T-route the address lines. Data you don't have to T-route because it's to each individual memory device. But the address, the control, and all these lines, they have to go to all of the memory devices. Right. And they typically would get T-routed for timing purposes. Well, one of the things the JEDEC committee figured out when they went to DDR3, and for the most part doubled the frequency, was that you can't just willy-nilly T-route stuff that has to be that short, because if you're going to T-route, all the T-routes have to be a lumped length, or you're going to get reflections at the T points. And that you could do that with DDR1 and 2 because the frequencies were low enough that the links could be long enough to get away with that. Well, they figured out with DDR3, you can't just willy-nilly do that. And yet, in spite of that, I can't tell you how many companies contacted me and said, Rick, we did a DDR3 layout and we're having problems. Can you have a look? Well, yeah, the problem is you T-routed. Well, you have to, right? No, you weren't supposed to. Had you read the notes, you would have realized that you were supposed to daisy chain everything. Well, that makes no sense. That creates timing problems. No, it doesn't, because it self-corrects. What? And people just don't get this.
Well, you're going to love this. I personally love this. So just yesterday, I recorded a podcast with two brilliant guys from Keysight. We talked
Yes.
about this exact issue because one of the guys, Randy White, is on the validation subcommittee at JEDEC.
Mhm.
And he talks about we were talking about memory design specifically, and we were talking about DDR5, and they're talking about things that they're doing with their software, specifically with ADS.
That's a
But
brilliant piece of software, by the way.
isn't it great?
Oh, it is.
And it's he was talking about the T routing
Mhm.
and how many people, when it goes up to the next, like DDR3, that people don't read the specs. And so he was talking about the importance of the JEDEC specs, but he was also talking about simulating before you do 6 spins, right?
Yes. Yes.
And so, and using their tools, obviously. But I think it's so interesting because I literally just had this conversation. I'm not sure which order, but I think there'll be some continuity between what
I'm
you're
sure
going to
there
teach
will.
and they're of course talking about DDR5, and they already started look at so, and every time they go up, all the
Right.
rules change. And if you
Right.
don't know that and know, I mean, if you just know to pay attention to the JEDEC specs,
Yep.
you'll be in way better shape.
Oh, absolutely.
And so
each iteration that comes along, the timing margins have to change. And even though as it gets faster, you have less headroom, there is still more headroom than people realize. Everybody I know exactly matches the length of traces. Well, there's several problems with that. One, outer layer transmission lines propagate at a faster rate than inner layer. So for example, if you have a 3-inch inner layer transmission line and you have a comparable one on the outer layer and you match them at 3 inches, the one on the outer layer will have a 1/4 of an inch error in its routing length because it propagates at a faster rate. It needed to be longer to be the same speed, to be the same, time.
right.
And people don't seem to know that. It's amazing how many people don't seem to realize timing doesn't have to be exact. It needs to be within the timing margins available within the memory and the controller. And they both have a certain amount of built-in timing margin. So lines can be off in length by a lot more than people realize.
Interesting.
And you need to match time, not length. And I'm going to talk about both.
Oh, you talked about this at Altium Live one year, and I thought that was so fascinating. Okay, well, I don't want to take your whole day, so give me 1, 2 for our listeners. I want to give them, if they can't join you at PCB West, because these aren't recorded. You've given so many great takeaways. Is there 1 or 2 grounding tips that our listeners can take away today and start applying?
Right. First and foremost, thank you, Ralph Morrison. The energy is in the fields, not in the voltage and current, which means it travels through the plastic of the circuit board. And people who understand that know exactly how they have to route relative to the planes to be able to control and contain the fields and not make crosstalk worse, not create reflection problems, not create EMI issues, et cetera, across this whole spectrum of concern. So keep in mind, that's where the fields are. So everything that you route, every single trace must reference a plane on the next layer of the board. Having 2 layers of signal and then a plane, sorry, bad practice. You do that, you're going to be begging for trouble. Now, you may get away with it. People get away with bad practices all the time. But the faster ICs get, the less chance you have of getting away with it next time.
Yep.
So understand, everything has to reference a plane. Can you reference power? You can reference power if ideally you're referencing the same power that generated the signal. Because since the energy is in the dielectric between the signal and the plane and the signal will have current flow in them, electron flow, that has to get back to the source and to the destination, and has to couple through the pins of the source and destination ICs. And the only way that's going to happen with a reference is if it's the same reference that generated the signal. So if it's a 3.3 volt signal, reference a 3.3 volt plane, not a 5 volt plane, not a 2.5 volt plane, and so on. If you reference ground, then it doesn't matter. Ground, everything is relative to ground. And I hate to use the word ground, but everybody else does. So
Yeah,
so that's one tip to keep.
that's a good one. Okay, give us another one, Rick Hartley.
When you never route across the split plane. I thought everyone knew this. I spent a few hours on a Zoom call just last week with a company that's having major EMI problems. I mean, they're out of spec by 20 some dB. I mean, they're so far over the limits, it's insane. And we went through their board stack up. And as we were going through, I saw several places where they had split power or split ground and had multiple traces routing across the split. Now, I'm not going to get into why, because it would be too lengthy of an explanation. You want to know why that's a problem? Look at the grounding class online. You know, come to think of it, I'm not sure.
You did one with Robert Faranik on split ground piece. So I will dig that out because I was really happy, and I could tell from his audience, they were like, what? And so for our listeners, I'll put that in the show notes as well as his
yes, that's a good
class.
idea. But anyway,
okay.
Don't route across splits in planes. If you must, and too many people split planes when they shouldn't. People think, oh, I've got analog and digital, I have to have two ground planes. Incorrect, you do not. I've put 1,000 volt RF stuff on the same board as digital electronics operating at gigabit speeds, and had a solid ground plane between the two and had zero problems. If you know what you're doing, it's not a problem. And that's the point that people need to understand. Just because analog devices, pardon me for damning analog devices, and other companies say you must split ground, you don't need to most of the time.
Well, and that's where I think the problem got started, or it's, you know, that's the feedback I've gotten. So yeah. So, okay. Myth busting. I love it. All right, Rick, I know we're running out of time, and I want you to talk just a little bit. You know, I can't remember how long ago, but in recent history, PCEA, which you're on the executive board of PCEA, which is the Printed Circuit Engineering Association, which is an association to serve not only engineers, but the industry. Their vision is similar to what I have here on the ecosystem, which is connect industry and engineers and board designers. And you have an amazing executive board. I used to be on it. I just ran out of bandwidth, but I'm a big fan.
And we miss you, by the way.
Thank you. And I miss you guys. If I can, I'm going to try to break off some of my time. I know. I would love it. Thank you. So anyways, for listeners, let's talk about the acquisition that PCEA made of UP Media, which is, I'm going to screw it up, Rick. They're the founders of PCB West, and they're also publishers of a magazine, Printed Circuit Fab.
It's design and Fab.
Thank you.
And then Circuits Assembly. So let me back up just one stride. I want to make sure everybody knows what PCA is. We're a trade association.
Okay.
And as you just said, and you're right on the money, we are there to link all aspects of industry. We want to link the designers to the fab, to the assembler, to the test people. We want to link all of them together. We want everybody to talk to everybody. And our goal is to create educational opportunities and inspire people to make those things happen.
Yes.
That's really what our mission. Membership is free. If you go to pcea.net, you can join PCEA for free. Corporate members pay a fee to be members, and they do so because they then have access to the membership. And the members then, and don't think of this as them prying in your life. Members, believe me, you want to have access to the fab houses and the assemblers and the CAD companies that are corporate members of PCEA. There's value in that. Mm-hmm. And there's educational opportunities for everybody. We're constantly increasing our educational parameters and so on. But when we bought UP Media, we bought the magazine, as you said, Printed Circuit Design and Fab Circuits Assembly. We bought both conferences, PCB East and PCB West. PCB West will be in 6 weeks, as you mentioned, in October in Santa Clara. This is like year 32 or 3
Yeah.
for the conference. I've lost track. It's been so long. I've attended every one except the very first one, and I've taught every year since 1998.
Yeah, and they haven't let you go yet,
No,
smart
not
people.
yet. Yeah, they're eventually going to kick me out, but as of now, I'm still.
I don't think it's going to happen.
And we also regenerated PCB East, which hasn't been around for a while. We had it in Massachusetts this past April, had a really good turnout, especially considering there was a COVID scare going on at the time.
Right.
I mean, it wasn't the greatest turnout in the world, let's be honest here, but it was better than we expected. And we were happy to see that. And we're going to do it again next year in Boxborough, Mass. And I don't remember the exact date. If you go to pcbeast.com, you'll find it.
And for our listeners, Rick's already sent these links to me. I'm going to put them in the show notes. So if you don't remember off the top of your head, they'll be there for you. If you're driving your car, working out, you can come back and look at the show notes later and get that information. So
one other thing we acquired from UP Media was the PCB Update newsletter. And one of my favorites that we acquired was the PCB chat that Mike Buteau does.
Oh, yeah. He has a great, in fact, I'll put that in the show notes below because Mike, like me, but different, right? Is
Different,
always
absolutely different, but also like you. Very
yes, yes. And I think we work well all together. It's
Oh,
not an
absolutely.
either or. We all bring different aspects, different people.
Yep.
And so I'm a big fan. I'm going to put PCB chat below, but yeah, absolutely go tap into all those resources.
Yep. And there's Printed Circuit University, which are a bunch of recorded classes that you can take for a small fee. And then on top of that, there's what we call PCB 2-Day. PCB 2-Day started as a 2-day class that I started teaching back in 2016 or 17. I can't remember, one of the two. And I did a few of them, and then they enlisted other people, Susie Webb and others, to do classes. They're now doing everything from 1 hour to 2 hour to 3 hour to full day to 2-day. And there's just this broad spectrum. Right now, the majority of them are online and can be taken as webinars. But when COVID allows, we're going to try to get back out into the world as well. Because I believe, and I know you do too, there's nothing like one-on-one. I mean, there's nothing like it.
Nothing like it. And we were talking about, how the industry has changed through COVID. Some of it's great, Rick, because some people would never get the budget or the opportunity to do in person. But if you have the opportunity, I feel like we've all been like me. I'm pretty extroverted, but even being indoors so much, I got used to it. Right. But the value you get of being in person, for example, if you go to Rick's class and then talking to Rick and asking him your specific application question, you just can't replicate that. You can't have a coffee or a beer or stumble across some gem that would have never happened had you not been networking. Well,
people talking to one another and saying, hey, what did you get from that? Oh, I got this. Oh, yes. I didn't get that, but I got this.
Yes.
And then later in the day, sitting in the bar talking. I mean, it's amazing.
It's amazing.
One does.
It will drive your career forward more than anything else I know. And I'm the proof in the pudding because my whole life is the value of the people I hang out with, that my amazing network. I have no illusions. I believe I bring something important to the table, but I think
very much so.
Thank you. But I think that the value of my network and the experts that I have the privilege of bringing to the engineering community, it's all networking. And so you just can't Can't underestimate that. Especially, I encourage young engineers where you guys are also digital, right?
Right.
Break the digital glass, you guys. Get out
Right.
there, shake some hands. It will change your career and your life. So,
I agree.
okay, Rick, I know that I need to let you go. And thank you so much. I
Thank
cannot
you.
wait to see you at PCB West. I'll just be up there for like a day and a half, but I will definitely look forward to seeing you and seeing all that. I know there's lots of, we didn't have time to talk about it, but all the great new additions to PCB West. It's
Yes.
only getting better and better. So
Yep.
again, to our listeners, again, Rick, thank you so much.
Thank you, Judy, and I appreciate your time more than you know.
Thank you. And me as well. To our
Thank you so
list,
much.
thank you. Our listeners, thank you so much for joining us today. I'm 100% sure you enjoyed this conversation with Rick Hartley. Make sure to go to PCB West, PCEA. We have lots of resources for you to tap into. We hope you can join us at PCB West. You will be forever grateful for tapping into that resource. Thanks for being with us today. And remember, always stay connected to the ecosystem.